Hello everyone. My name is Jasmeet, and I'm currently working as a robotics engineer at Peer Robotics, where we develop collaborative AMRs for warehouse applications. And in the throughout the product, we keep human-robot interaction in mind. And today in this talk, I'll be talking about a project that I worked on during Google Summer of Code this year with the Gazebo team at Open Robotics. This project was about developing a feature that allows Gazebo to automatically compute moments of inertia for robotic links. So let's get started. So, like any other project, let's first try to resonate with the problem and the motivation behind the project. And for that, let's start with a basic refresher of what is moments of inertia. And we'll just be going through some practical examples just for a revision. Let's see. So for example, in this GIF here, you can see moment of inertia is what causes the hollow disk to reach the end of the inclined plane later than the solid disk. Another practical example would be this scenario where the person speeds up with folded hands and slows down with the hands widespread. Another practical, kind of practical example would be this scenario where you can see a good knowledge of moment of inertia saved the life of Roadrunner, and bad knowledge of moment of inertia caused the unfortunate end for Wile E. Coyote. So yeah, so basically from this we can conclude that moment of inertia is something that can describe how a rigid body would act under rotation. If we consider theoretically, the moment of inertia of a rigid body can be represented by this 3x3 matrix. This is known as the inertia matrix, or also sometimes called as the inertia tensor. The diagonal elements of this matrix are known as the moments of inertia, and they actually represent the resistance that the rigid body will provide to a rotation across the selected axes. The off-diagonal elements in this matrix are known as the products of inertia, and they represent the mass distribution, or they comment about the symmetric or the asymmetric properties of that rigid body about those axes. This matrix is also symmetric about the diagonal. So so for example, iyx or ixy, they will be equal. And if the axes are aligned with the principal axis of the rigid body, the products of inertia become zero. So now some might think that why do we care about moment of inertia so much in robotics? For that, let me show you an example. So this is so shout outs to some of my juniors who allowed me to tamper with the inertial parameters of their project only for research purposes. And here you can see we have changed the inertial, like the mass and the inertial properties of some of the legs of that spider robot. And instead of going forward, it tries to go up and eventually ends up upside down, which is unlike any real spider. If you can see, so that's why you can see that accurate and physically plausible inertia values are required for an accurate simulation, and then eventually for transfer of the software to the actual hardware. Now let's see how do we describe the moment of inertia for a link in Gazebo simulations. So for that, like every simulation, we describe it using the SDFormat. And in that, for describing the inertial of the link, we need 6 values from the inertia matrix. 3 for the moments of inertia and 3 for the products of inertia. We only need 3 because the matrix is symmetric about the diagonal. And apart from that, we also need the mass values in kg and the pose of the center of mass, which is also known as the inertial pose in the link frame. Okay, so this is how the whole inertial element for a link might look like. And now let's discuss the actual pain points of the users, which are the existing workflows to get the accurate inertial values for the robotic links. So one of those workflows is that many people design their robots using some kind of CAD software like Fusion 360 or SolidWorks, and they provide plugins for exporting the URDF that already calculate the inertias and put those in the SDF or the URDF that is exported. Another way would be, so for example, if you design the robot using some other software for say Blender or FreeCAD, they might not have the plugin to export the URDF. In those scenarios, you can use external mesh processing software like MeshLab to you can just load the mesh and apply some kind of mesh processing, and you can get the moment of inertia values from those software. Another way would be to just stick with the default values that Gazebo provides, but they might not be fitting for all situations because they just like put mass as 1 kg and unit values for the moment of inertia and 0 for the products of inertia. And last and the most painful way would be to do manual calculations. And this is the one which I try to avoid the most because for the primitive geometries it might work, but for mesh it's a nightmare. So yeah, these are the existing problems, and these problems or these workflows bring the motivation for this project, and that is that physically plausible inertial values are required for an accurate simulation. And these inertial values, they might be difficult to visualize, and if you have wrong inertial values, it might be hard to debug why the simulation is going wrong. It might be hard to pinpoint exactly which link has the wrong inertial values and which is causing the problem. And finally, the current solutions or the existing workflows, they cause a dependency on third-party software, or they might not be fitting for every situation, like manual calculations or going with the default values. So this is how we get to the problem and the motivation behind the project. And that leads us to the discussion of the solution. And that too first from the user's perspective. How do we want the user to use the feature? And that will lead us to the development phase later on. So let's first discuss. As we go through this section, we'll be filling up the inertial element of this link with all the new introduced elements or the attributes. So first, we wanted this feature to be easily enabled or disabled by the user, just like a press of a button. So for that, we introduced an auto attribute for the inertial tag, which you can just set to true or false to enable or disable the automatic calculation for the link. Apart from that, some kind of input from the user is absolutely required to get some information about the mass properties of the link. It could be either the mass or the density or the volume. So we went with the most intuitive one, which is the density, because you only need to know the type of the material and you know the density of that material. So if you know that this link would be made from aluminum or from steel, you know the density, you can just put the density of that material in the collision tag, and that will be used for calculation of the inertia. So here you can see we have introduced a density element for the collision tag, where you can just input any float value for the density. By default, the density of water is considered, which is 1000 kgs per meter cube. And after that, we didn't want to restrict the user to describing only one collision per link or using only one kind of geometry. So for that, we have allowed the user to describe a link with multiple collisions having different density values and different geometry types. So here you can see like this link is made from 2 collisions having different densities and different geometry types. All this support is provided, and behind the curtains, the different inertial values for each of the collisions, they are aggregated, and then finally the inertial for the whole link is set. So yeah, this is the summary of the whole user perspective solution. And now that we have in mind what do we want as the final result, we can move on to the development phase. And here I'll be going through what is happening behind the curtains. So yeah, so for the primitive geometries, the parsing of all the newly added elements and the attributes and all the moment of inertia calculations, they are provided integrated inside libSDFormat, which is the parser for SDFormat. And we did this because this would allow different simulation platforms, not only Gazebo, but there are many other platforms that also use SDFormat to utilize this feature. Apart from that, so there are existing mass matrix functions in the gzmath library which were used for the primitive geometries, because they are just like, you just have the equations, you have to input the values, and they give you the moment of inertia for that particular geometry. These primitive geometries include from left to the right, ellipsoid, sphere, cube, cylinder, and capsule. These are the current primitive geometry types that are supported by gzsim, and this is the world that opens up when you do gzsim shapes.sdf. This is an example world in gzsim. So these are all supported with the primitive geometries. And now another most common geometry type is 3D meshes, which is used. And for that, we have included a callback based mechanism in libSDFormat. This was done because different simulation platforms might have different solutions for the moment of inertia calculation. So we didn't want to like restrict the simulation platforms with only one kind of calculator, and also this would prevent any kind of burden on libSDFormat for adding dependencies or something like that, and keep it lightweight as it is. So that's why we opted for a callback based mechanism where libSDFormat would just call a function with a given footprint, and that function could be inside any simulation platform that is being used with libSDFormat. So for Gazebo, our implementation can be found in a mesh inertia calculator class inside the gzsim repo. And for that, initially we explored the process of 3D voxelization of meshes for the inertia calculation. If you think about it, this could be one of the most intuitive way to calculate inertia, because if you remember from high school, any kind of integration process begins with breaking down an area or volume into small chunks. And this is what voxelization does. It breaks down the mesh into small voxels. You know the voxel size? It's basically a cube. You can calculate the inertia of each cube, and you can just aggregate the result and get the final inertia for the mesh. But there is a catch. So we were exploring OpenVDB library for voxelization, and that library depends on another library which is for use for threading, and it's TBB. But the binaries of both these libraries available for Ubuntu Jammy, the Ubuntu 22 version which we are targeting for GZ Harmonic, they are incompatible. So if you just download the libraries from the Ubuntu app repositories, it won't work. You would have to download it from source, build it from source, add it to the gzsim repository, and it's a headache. So we have to avoid it at all costs. So this idea was scrapped. And next, we moved on to a numerical method, which was presented in this paper by David Eberle. And this method is already commonly used in many mesh processing libraries. For example, there is a common mesh processing library called TriMesh, which is Python based, and it uses the same method. So, and it uses Gauss theorem and Green's theorem to convert the volume integrals to 2D and then one-dimensional integrals, which you can just calculate. So I cannot claim to like understand the whole mathematics here, but for people like me, this paper had a pseudocode which I can completely understand and was able to convert it to C++ and include it in gzsim. And now we can see like some of the demos. So here you can see on the left side, the yellow cylinder, it is having an inertia that is automatically computed. And on the right side, the cylinder has an inertia that has the default values. So you can right away see that on the left side, the automatically computed values are more suited for this scenario, because on the right side, the cylinder will have 1 kg of mass, which might not be the case. Another example would be, like I said, there are no restrictions. You can define multiple collisions inside the same link having different densities. And this is one of those examples. This link was made using a cube and a cylinder, and both of them had different densities. And you can see like there is an aggregated final inertial element that was set for this whole link. Apart from that, so this is an example like the one we saw, but like the practical example that we saw in the beginning of the presentation. So, and this is also an example world that comes with GZ Harmonic, so you can just open it up and like experiment with it. On the rightmost side, you can see the yellow cylinder, which is actually a mesh of a hollow cylinder. And like the practical examples, we can see that it reaches the end of the inclined plane at the very last. And apart from that, there is this demo which uses primitive shapes. Both of these are pendulums, similar structure, but the difference is in the inertial properties, which are automatically computed. For the right side, you can see the center of mass of the pendulum is towards the end with the bob. And for the left side, you can see the center of mass is closer to the pivot point. And this is also similar to the practical example that we saw in the beginning, where the person speeds up with hands folded and slows down with the hands widespread. Similarly, you can see like the mass is concentrated towards the pivot point, and that pendulum is oscillating faster as compared to the other one. So this is also physically accurate, and the inertia is computed automatically for both of these pendulums. Another example would be this scenario where it's kind of a double pendulum structure, and this was included in the Gazebo Harmonic demo world. And here you can see some of you might recognize this sculpture from Iron Man 2 movies. And so basically the inertia for this structure is also automatically computed. You just like leave it hanging and it will perpetually move because there is no friction added at the moment. But you can find this in the gazebo harmonic demo world. You go into the kitchen and you will find this on the table. Another example would be this fidget spinner, which is actually a mesh for whom the inertia was calculated automatically. And this can be found in the same demo world in the office desk. And shout out to another GSOC project, which was made this year only, that allows you to apply force on objects using mouse drag. So that's what I'm doing here. You can see like this is the fidget spinner, and I'm applying a force on the fidget spinner using my mouse drag, and it's rotating. So you can just open up the simulation, go to the office, and start playing with the fidget spinner in simulation. So with that, we complete the development phase, and we can also see the fruitful results that we got from the development phase. Like we can see like the inertial values that we get are accurate up to some extent, and we have also like to define it in a quantitative way. We experimented with different vertex counts of meshes, and we found that for the mesh inertia calculator, if we use higher vertex count for the mesh, we can get values close up to like 0.00 tolerance of the theoretically computed values. And then finally comes the testing phase, where you all guys come in and you can like test out this feature. This comes with the Gazebo Harmonic release, and it's already released, so you can just go and try out the feature and see if it doesn't work or your laptop ends up burning or something like that. You can just try out the feature, and you can and if it doesn't work, you know who to blame, and you can just like contact me, or we can just start working on the issues together, and we can like try to solve the problems. So finally, these are all the resources that are available for reading more about the feature. One would be on the Gazebo Discourse. You can find a community post regarding the feature, which explains all the examples and how to use it. And there is another SDFormat proposal which was made for adding new elements and attributes to the SDFormat specification. And this proposal discusses in depth about the implementation, how the callback mechanism works, and how the API was formed for the whole feature. And after that, you can also find tutorials in the GZSIM repository, which shows all the example worlds and how you can use that, how you can experiment with them. And then finally, like any other feature, you can go through the Gazebo or the SDFormat source code and try to go through the code, look and see how the things are working. So yeah, thank you.
Thank you, Jasmeet. This feature is a great addition to Gazebo Harmonic, and you guys should try it out. We have time for one quick question. Anybody has any question?
Thank you for this great talk, Jasmeet. Like this feature is actually really amazing to see implemented in Gazebo already. So I have not much of a question, but actually a kind of excitement about trying out this idea about adding continuum robotic solutions to Gazebo. So if you have actually already implemented auto inertia calculations, then I was wondering if you have a limit on how much of a fidelity you can offer with these simulations. Like what is the limit that you can cross to have actually to have your laptop not crash and burn, basically, because a lot of links will be there. And imagine a flexible wing structure or something, right, that you want to simulate in Gazebo. So I was wondering if you have some thoughts on that.
Yeah, so from what I have tried, like I have tried multiple examples and in multiple scenarios with different kinds of meshes and high vertex counts. From what I have seen, I haven't faced much of an issue with the like Gazebo crashing or like the calculations taking time, because the numerical method which we are finally now using, the voxelization method might have been kind of that, because in that you have to create a voxel grid, you have to intersect it with the mesh, and a whole lot of computation is involved. But for the numerical method, it's not that that slow because it's just like crunching numbers, and every computer can do that very fast. So, but if you have a higher number of mesh count, then it might slow down the calculations. But for that, the Gazebo team, it recommends using primitive shapes for the collision because it is actually used for all kinds of physics calculations. So not only inertia calculations, but anything related to physics, the collision geometry will be used. So the Gazebo team, they recommend using primitive geometries, but you can also use mesh, and I haven't faced any issues with all the examples or all the scenarios. Like you can see the Gazebo harmonic demo world, it was quite a heavy world, and even there, like the automatic calculations were working fine. And if you might face some issues regarding that in future, we are also working on a command line utility where you can just like input the SDF file, it will give you the computed values, you can just put it in the SDF file and then use it afterwards. So it won't compute every time you open GCSIM. So this is also upcoming feature.
Thank you, Jasmeet, for the answer and the talk. So give a big round of applause for Jasmeet.
Thank you.